Hello everyone. Welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have Professor Dingwen from the Indiana University to give us this talk. Professor Tao is currently associate professor at the Indiana University Bloomington, and he directs the high performance data analytics and the computing lab. He received a PhD degree in computer science from the University of California, Riverside, and a bachelor degree in mathematics from the University of Science and Technology of China. He's the recipient of the various awards, including NSF Career Award, Amazon Research Award, Meta Research Award, and the 100 Awards, IEEE Computer Society, TC, HPC Early Career Research Award, NSF CI Award, and the IEEE Cluster Best Paper Award. And he's currently serving as the associate editor of the IEEE Transaction on Parallel and Distributed Systems. And he also serves as the program chair of the IEEE ScaleCon, the BSD and the IWBDR workshops and other IEEE ACM conferences. He's also a reviewer program committee member, session chair of major HPC conferences such as SC, HBT, HBDC, ICS, and so on. And he's the senior member of the ACM and the IEEE. So now let's welcome Professor Tao to give us this talk.
Okay, so thanks for the kind introduction, Bo, and also thanks for invitation. So today I want to talk something about our recent work related to improving performance and scalability of distributed deep learning system through like efficient data management, specifically some relate to my core research about data compression techniques. So because as I mentioned, I'm a high-performance computing person. I working in supercomputing, HPC area since my PhD studies. So I want to first give you some like idea about high-performance computing system, the development trend in the past 10 years. So from the table, let me just get like a laser. Okay, so this table actually shows the past 10 years HPC system different specs, right? Specifications. So you can see they are like a memory size, they are like a peak performance, they are storage, bandwidth, they are memory size. So from the table, you probably will find that the peak performance here, this is a peak performance, right? So compared to the storage bandwidth, and the memory size compared to the storage bandwidth is increasing every year, right? Or every several years for the new machines, which means that the computing capability is increasing, but the storage capacity and storage bandwidth are developing relatively slower, right? So slowly. So this gives us some idea like we have very powerful machines can help us to do a very large scale computations, no matter in the scientific computing or artificial intelligence, because people are now using the HPC system supercomputing to do the machine learning. I will give the idea why it is needed, right? But the storage things, the data movement, right, are challenging. So I think the data movement is not only challenging in the hardware chips, but also in the whole system side, right? And the different countries and the regions are trying to build the exascale supercomputers, which is capable of 10 to 15 floating point per second, right? So which is a very powerful machine, but the storage is a problem. And the second slide I'm showing here is about the heterogeneity of the HPC system, right? People are talking about heterogeneous computing. From the system design perspective, the HPC system is also very heterogeneous. So there are like a GPU, right? For example, the top 10 system in the top 500 list, right? So showing that 70 or 80% of the machines are based on the GPUs. because GPUs are now very powerful, right? So AI people, almost everyone is using GPU. For HPC, for scientific computing people, some code are still CPU based, but people are trying to port the code to the GPU side, right? And also you can see like the memory storage hierarchy are also becoming complex. So there are like some burst buffer, there is some like a remote file system and local scratch storage, right? Which makes the data movement even challenging. And also people are trying to investigate the FPGA-based or DPU-based smart NIC in the system, which can help the computing to happen in the near the networking, right? Reduce some like workload for CPU and GPUs. But those like hardware, you also need to handle the data movement. So I also want to give you some perspective from like application point of view, because I just talked about something related to the system design, right? So for the application side, for example, I collaborated with different application people. One example is a cosmology simulation, right? So we published a series of paper regarding how to help a large scale cosmology simulation to handle the data, right? So the astrophysics people trying to use this simulation to understand the universe evolution, right? For example, this code called HACC, right? HACC. Such simulation with 1 trillion of the particles can generate more than 20 petabytes of data, while the supercomputer, the last generation supercomputer Mira in Argonne National Lab, can only have like 26 petabytes storage space, which means that one single simulation, large scale real simulation, could dominate more than 80% of the storage space, right? But Mira has been retired. So this is just for example. So for another example, today is more and more people are trying to understand the climate change things, right? Such as like a global warming. Scientists are using the large scale climate simulation to understand or to help with this problem. So if, for example, using the NSF Blue Water supercomputer, it's also a retired supercomputer built in University of Illinois, right? So it takes more than 5 hours to save the data from the memory to the disk to the parallel file system for this simulation. And the people are spend more time or more money, right, to build the hardware system for the storage. And another example is not about the computation, but also about the experiment, right, the instrument. So for example, here, like a high energy physics people are using this is the advanced fountain south at Argonne National Lab. So it's updated version, upgraded version called APSU, right? So this X-ray beams experiment can generate more than hundreds of like terabytes for only like a one-time or scan of the brain's imaging, right? So they also have a very strong motivation to reduce the data size. And also this is for the data generation. If you want to move the data from the generator to the data processor, right? For example, supercomputer. So Argonne National Lab has a APSU and also has a Mira supercomputer, right? So you can think about like if you want to move this data between these two facilities, the network bandwidth is kind of limited, right? So some people are joking that so even using the networking to transfer data, probably you can just use your portable USB or like some other devices to directly copy and plug into the machine, right? But it's not possible because HPC machine is is highly protected. No one can, except the administrative people, you cannot approach to the machine, right? So if you want to take a look at the machine, you just you need to apply for some permissions. So another research topic I'm focusing, and today I'm going to talk about, right? So it's a system issue when using large AI models. I think here people are attending this talk is very familiar with AI, artificial intelligence, and why we want it to be as efficient as possible, right? Because the seminar talk is efficient AI. So here just some like a quick motivation. So the model is becoming large. Their like a memory consumption is large. increasing larger and larger, right? And the GPU memory is limited, right? Sometimes when you try to training a large model, you will find, okay, the batch size, you cannot increase that. Otherwise, that would be out of memory, right? So the PyTorch or TensorFlow will be just automatically exited because of the memory cannot host, right? And so to this end, we propose some solution. So I will mention that in the later slides about how we can reduce the memory consumption to increase the batch size for larger scale training, and we can overall increase the training throughput. This is the first problem for the memory issue. And another thing is like we have some like sparse training. Especially we focus on the backward propagation because we identify that in the traditional CNN training, the backward phase consume a lot of like time and the flops. And if we can reduce the model size, right? People are doing the pruning or like model compression. So we can also reduce the training overall time and the backward propagation time, right? But how to incorporate the reduced model and the backward propagation, that's a technical issue. So we achieved that in a previous paper. So I can quickly mention that later. And another issue is the I/O issue. So because as I mentioned, if you are doing the artificial AI model training, DN model training, now maybe the large language model training, LLM training, right? So you need to have a large scale data set. And those data set different from like your own laptop or like a workstation. The data is saved in the remote file system because it's a really large terabyte scale, right? So cannot be saved in your local disk. So you have to read the data from the remote file system, and during the training, the data needs to be shuffled, right, and needs to be random accessed. So we should introduce a lot of like a time overhead and the reading data, loading data overhead, right? So in another work, we are trying to solve this issue because of the large data set, especially AI for science, right? People are trying to use AI for the scientific problem, and the scientific data set, as I just mentioned, is super large, right? High resolution, high dimension. And generated by the instrument by simulation, right? Saved in the HPC system. So if you want to read those data during the training phase, that's challenging. Okay. So I want to quickly mention the thing I've been working for a couple of years. I think more than 5 years, 7, 8 years. And this is a technique we call error bounded lossy compression to help reduce the data size significantly, but still can maintain the high fidelity of the data set, right? Or the accuracy of the data set, or the information within the data set, right? So, but the first question is like, why we are trying to use a lossy compression? Why not using the lossless compression, right? So the lossless compression actually is widely adopted everywhere. When you try to send the file image or like a doc, right, to your colleagues, to your collaborators, and you maybe first try to archive, right, different small size of the data or files, and then try to compress that, use maybe gzip, right, or WinIR, or like those compressors, and then send that to people, right? And those compressors actually are not lossless compression, because after decompression, the data information is exactly the same as the original file, right? But different from lossless compression. Lossy compression is after decompression, the data is changed, is alternated. But think about like image compression, video compression, right? So, or even like audio compression. So you can still recognize the information within the data, but the quality could be adapted or changed, right? For example, like our Zoom meeting, right? If my network is not that good, you can see my resolution will be automatically decreased, right? But the problem is like for the scientific computing or for the artificial intelligence problem, AI problems, right? So sometimes the image compression is not enough, because it can only preserve the information from like the visual quality perspective. But a lot of problem is not a visual problem, right? So for scientific problem, you have like a lot of like data, like a DNA data or like those data, right? So you have to make sure like the scientific information is maintained. So we have been working on techniques. We are not the first inventor, but I think we are the first group of people have been working here for a long time, right? So there is like another error-bounded lossy compression. So why this is error-bounded? So people can provide a different error controlling scheme. For example, you can control the absolute error, right? For each data point, you can control the each point like a relative error bound. You can control the RMSE or L2 norm based error, right? And sometimes if you want to control the data to some specifically size, right? So you can do that with a fixed bit rate compression, right? And all those compression error controlling formats or like modes, right? Tries to make sure like the post-analysis requirements can be satisfied. For example, in the AI problem, right? So compress the input data, compress the gradient data, compress the activation data. When you're trying to understand if this compression is good, you're not going to directly investigate the data itself, right? You are trying to understand, okay, the overall model accuracy, right? So it's the same thing in the scientific computing. So you are trying to understand not only the data itself, but also after some like analysis or visualization or like a post-analysis process, right? So, so we have we have collaborated with the Argonne National Lab during the, as I mentioned, past 7 to 8 years, and we have developed a lossy compression called the SC lossy compression, and this compression is based on the prediction approach, and it can strictly control the global upper bound for the compression error, and also we have implemented it on the CPU, multi-cores, OpenMP, right, and the GPUs, CUDA. We are now trying to implement the AMD GPU version, and also we have some prototype for like a PGA. And we integrate that in the different I/O libraries. For example, HDF5, Audius, PNCDF. Those libraries have been widely used by the domain people and also maybe the AI people. I know some people are using HDF5 during their like CN training or DN training, right? So because HDF5 is very organized hierarchical data format. So here I want to quickly mention what is our compression pipeline. So I'm going to quickly talk about that because this is not focused on the talk, but I just want to give you some idea about our compression, and then I will say how we use that in our machine learning system, right, to accelerate the distributed training. So the idea is pretty straightforward. So it's, as I mentioned, it's like a prediction-based state technology, right? So you are trying to predict the data based on the nearby information, right? And this stage, we usually call it a decorrelation stage because data has very strong correlation. So if you can decorrelate it as much as possible, then you can gain some like a compression ratio, right? Because original data just use a very extreme example. For example, if the data it's a 2D data, if the value, or let's say if the 1D data, right? So if the value is exactly the same as its coordinate, right? 1, 2, 3, 4, 5, you never will save the data value, right? You just save the formula, right? You just save this like functions, right? So because the data is strongly linear correlated, right? So the idea is similar here. We are trying to identify what's the functionality, what's the correlation within the data set, but definitely we cannot completely remove the correlation, right? We still remain some correlation. So that's why the second step, we are using the quantization. We are trying to quantize the prediction error, right, between the original data and our prediction error, right? Original data and predicted data, right? So we are trying to quantize the difference because we are not using the original floating point format. We're trying to use integer or other like a data format, right? And then after that, we can do some lossless encoding, entropy encoding, GZ, persistent, those like a pipeline. I want to give note here, because this pipeline actually is quite flexible, because for different type of the data set, you can definitely use different predictors, right? So by default, we are using a very simple Lorenzo predictor, just to use a neighboring points to make a very simple, like a linear function. But definitely you can even use like a machine learning or neural network here, right, to make a prediction. That's just a trade-off between the prediction accuracy and the time cost, right? As much as you can predict, or as accurate as you can predict, then the remaining data will be small. After quantization, there will be close to zero. Then compression ratio will be high, right? That's easy to understand. So I want to give like some idea about how our compression can be utilized and our like targets. So the software, as Bo mentioned in the beginning, we won the R&D 100 award because of its I would like to say it's pretty good engineered, and we have like some application people use that, and we have like a different CPU GPU version, right? And also we recently identify some very nice use cases. For example, in HPC area, reducing the storage demand, right, and accelerating I/O and communication. So I will have a work regarding like reducing the communication in the machine learning training, right? So reducing the I/O and the communication is very important for the large scale computation. And also we can accelerating visualization, because previously when you try to visualize something, you save the data in the disk. But now we can save the compressed data in the memory, right? So we don't need to read the data. We can online visualize the data, and we can reduce the streaming intensity. We can run larger problems. We can accelerate the checkpoint restart speed, right? For example, running the larger problem, there like was a Golden Bear Prize paper talking about using compression can help them double the problem size of simulating an earthquake. I think from China, right? So they're using customized lossy compression, right? The problem size can be double, the resolution can be double. So to help them to won the Golden Bear Prize. Just for information, Golden Bear Prize is a highest honor in the high performance computing application development. People trying to develop a lot of applications, right? But if they can run very large scale in the whole system, for example, running using the whole frontier supercomputer, exact scale supercomputer, right? And get a very good scientific discovery, then you can have a chance to win this Golden Bear Prize. And also AI use cases, we recently have been heavily working on that. For example, we can do the DN model compression, right? Because DN data are all like a floating point data, most likely, right? And we can accelerating the training, the pipeline. For example, we accelerate the data reading, loading, as I mentioned, and also we can reduce the DN memory consumption, just as mentioned, and we can accelerate distributed training to reduce the I/O or reduce the communication, especially communication. So I will talk about my collaboration with Facebook. So they are having a very heavy communication in training a recommendation model. So using compression can help them to achieve some performance. So here are some like my projects, and as I mentioned, I spent most of time previously developing the compression. So we have like different types of compression. The first one, I can give a very quick introduction, because I think I'm kind of proud of that, because we are trying to build a community and push and push the compression to the more like a customer side, because different people have different requirement, right? So how to design their like specific compression is a problem, right? Not just using the general compressor, because general compressor definitely is not good for every cases, right? For some specific cases, for example, the DN activation data, right? Or like gradient data, right? So how you can find the best or near optimal compressor, right? So we have like some framework or ecosystem, which this project is just founded. And also I'm working on some like a system for machine learning, especially accelerating communication, as I mentioned, right? In the deep learning model training. And we are trying to work with DOE people to set up like AI and the simulation benchmark, right? To help scientists to reproduce the AI model performance accuracy as much as possible. So here is one quick slide I just mentioned. So we recently got like a grant from NSF to build the framework, right? Can help user to streamline or to ease their like effort on developing specialized compression, right? The reason we are trying to develop a special compression here is a quick example, right? So if we are using general compressor, the ratio is just 27, but if we are using the specific compressor, we are optimized. It can achieve almost double compression ratio. But this effort takes us so much time, right? So we spend maybe 1 year or sometimes even 1.5 years working with application people, investigate the data feature and understand that they are like accuracy need or they are like a fidelity requirement. And then we improve our compression and we implement that and we integrate that into their like application. Then we will identify, okay, this is a good strategy, right? So this is the timeline really, expensive. So we're trying to develop a software to do some automation, right? The approach could be like we want to develop some like high level interface, right? So create a compressor from high level language such as Python. Right now, people are just to use write C and C++ code to enable compression. That's not easy. We are trying to follow like a PyTorch step, right, to build a high level programming interfaces, right? So you can easily compose the compression you want and then generate the high performance code from the backend library. So the second is like we are trying to have like a CPU, GPU backend modules, right? The front end can link with the backend, and eventually we are trying to visualize and assess the quality and provide the GUI tools, right? This is like our hope is to make a community tools and the framework, right? People can easily to use the software. And we just have our first kickoff meeting, invite different people, different compressor developers. Okay, so let me go into the more details about some deep learning stuff, right? As I mentioned in the title, deep learning systems. So we have published some works in the different venues, such as like in the HPC venue, in the hardware, software, code design part, and also supercomputing venue, VLDB. This work I will talk about that, and we also work on some like paper. Let me go into some details. Okay, so I think I still have like maybe 20 or 25 minutes to talk about 3 works. Right, every work I may spend 5 to 8 minutes to talk about that. So the first work is by using lossy compression. Right, so that's the reason why I want to give the idea what is using lossy compression, right, rather than directly talk about this work, because people may have some like confusion. What is lossy compression, right? So by using error bounded lossy compression to achieve like memory efficient deep learning training. So I think the motivation I just mentioned, right? So GPU memory is limited, and training with larger batch size, right? So it's really needed for many scenarios, right? So I know some machine learning optimization people are trying to use different approach to reduce the required batch size, but in general, batch size is still very important, right? In many cases, you need a large batch size for faster convergence and for the better accuracy, right? So, so how we solve this problem? Or at least how to mitigate this challenge, right? So I think the idea is pretty straightforward, as the title indicated, using lossy compression. Because when you try to train the model generate the training forward propagation phase generate a lot of like intermediate data, right? So for example, activation data in the CNN. Now I think the transformer also have like some activation data, right? So you have to withhold those like data in the memory, because this data needs to be used in the backward propagation. And if the model is deeper and it's deep, right, and the data withhold is larger, right? So our idea is what about let's just compress the data during the forward propagation, and during the backward propagation, let's decompress that and reuse that, right? And some layer, I think in the current PyTorch framework or TensorFlow framework, so the framework doesn't store the data, doesn't save the data. It's just recompute because the data can be quickly regenerated, right? So, but our strategy can be orthogonal to those like a strategy. For example, moving the data from GPU to CPU, right? And as I mentioned, just recomputation. So our focus is just to focus on the data is saved in the forward propagation, right? But the idea is pretty straightforward. What is the challenge here? The challenge here, I think there are several points. The first point is like, because we are using lossy compression, right? How to control the, as I mentioned, error bound, right? How I can set up an error bound, or how can I control the error propagation to ensure the model training still be okay, right? Not accuracy significantly degraded. Okay, and also, as I mentioned, because I compress the activation data itself, but eventually I want to investigate the gradient, investigate the model accuracy, right? How to link them, and also how I can like online adaptively configure those like setups, right? Not like offline setup and online use that all the time, right? So those, I think the challenge is not just incorporate the lossy compression in the framework, but how I can accurately use that, how I can adaptively use that, right? That's a challenge. So I think in our framework, we have different phases or different components. For example, we're trying to collect the parameter for analysis and updating compression configurations, right? I will have like some formulas to do this like analysis and configuration. And also after that, I want to estimate the acceptable sigma in the gradient. So sigma means like what's the loss that can be accepted in the gradient, right? And then I want to estimate, okay, because the activation to gradient, but now I going back order, right? I first understand the gradient, the accuracy loss tolerance, right? And then I going, and I need an analysis to know like the activation loss tolerant, right? And I want to estimate the error bound. And after that, I want to use the lossy compression, but here we are using the GPU lossy compression, right? So which means that the GPU compression performance needs to be optimized. And for this specifically case, we need to preserve some zeros, because in our investigation, if we change the zeros to non-zero or change non-zero to zeros, the accuracy will be significantly degraded. But in the original compression design, we didn't consider this constraint, right? So zero could change to non-zero, non-zero could change to zero, because we only set up the error bound, right? We didn't set up any other like constraint. So we also need to modify our lossy compression and do a good GPU implementation. And here are like some design details. As I mentioned, we do some like offline parameter collection, semi-online parallel collections, for example, batch size or like activation data sparsity, like average loss, those like information. And then we are doing the gradient assessment, right? We are trying to compute the sigma based on the parameters and the empirical experience. And also we trying to derive a formula from the sigma to the error bound that we use for the activation data. And eventually, as I mentioned, we need to modify QSC. So QSC is the SC GPU version, CUDA version of the SC, right? To compress the sparse floating point data. And we are trying to change the configuration every other like several iterations during the training. And here like some quick evaluation. I try to make the each paper, right? So condensed as possible because I want to present the idea. So the details you can take a look at the paper, or we can discuss offline. So here are some like a quick evaluation results. So you can see that for some like cases, but to be honest, this is the work we done like three years ago, right? So the model we are using here is still kind of like old. I haven't like asked a student to update this work to some new models, but I think it's the time to do that. For example, we're training some like a large language model, but so far we haven't got a bandwidth to do that. But here, bear me like I'm showing like some old model, ResNet 50, right? It's kind of old model, even like have some ResNet, it's very old model. So, but the idea I think can be demonstrated. Like we can achieve the high compression ratio, and as I mentioned, so we can almost maintain the model accuracy, testing accuracy, right? And as we reduce the memory consumption by more than 10 times, which means that we can almost increase the batch size by at least 5 to 10 times, right? And compared to the other compression approach, so I think this is a paper published in ISCA. So this is a hardware solution. So it's tried to use a JPEG activation compressor, right, to modify the JPEG compressor to compress the activation. And it specifically proposed a hardware component in the GPU to do that. And it compare with the software JPEG and say, okay, so we achieve some performance gain and publish in the ISCA. But we are purely pure software solution. We don't have like any hardware specific design. But definitely, if you want, right? So that's the purpose. Like I'm also doing some FPGA or ASIC design for the compressor. We can also put our compressor into the hardware, right? But in this work, we are pure like software solution without any like hardware design, right? So we compare with the JPEG Act, you can see like our compression ratio is even higher and with the same accuracy, and that means we can support large batch size. And with a larger batch size, we can achieve a higher overall throughput. And here one note is like we still introduce the compression overhead, right? It's not a free lunch. So we have some like compression overhead, but this overhead has been offset by the higher throughput, right? So you pay something, you gain something. But as I mentioned, if we can offload this compression to the hardware or maybe other like a component, reduce this compression overhead, you can gain more, right? So that's a trade-off here. And also we compare with some different solutions, as I mentioned, right? So for example, this migration solution means that you move the data between CPU and GPU, right? If you do not have enough GPU memory, you just put the data to the CPU memory. And once you need that, you just move data from CPU memory to GPU memory. We compare with this solution. So our rationale here is like a computation power, as I mentioned at the beginning, right? Computation power is developing faster than the data than the hardware bandwidth, right? The CPU, GPU, the bandwidth is included, right? So for example, CPU, GPU now using PCIe 4 is only about 32 to 40 gigabytes per second, right? Or maybe NVLink is 50, right? But that's a specific design like hardware interconnect, right? But the computation speed now hundreds of gigabytes for compression at least, right? So if we have that deep optimization, we can even achieve like 300 or 400 gigabytes. For example, NVIDIA's own like a NVComp compressor, right? So it can achieve more than about 300 gigabytes per second. So that's something I want to mention here, because if you are trying to use compression, then you will have a question, okay, how fast the compressor it is, right? I can let you know the GPU compressor on the A100 or even H100, it could be hundreds of gigabytes, but moving the data is only tens of gigabytes. So that's a trade-off here. Okay. So then let me quickly talk about our second work is accelerating communication in deep learning recommendation model training through the frequency-aware lossy compression. This is a work collaborated with Facebook, and also it's a part of my Meta Research Award. So the motivation is pretty straightforward. So Meta is using deep learning recommendation model for their business. So there's I mean, this machine learning task is there like a revenue focus like a task, right? So help them to earn money. Okay, so run it as fast as possible, helps them to generate a profit, right? Revenue. So this is very important for their business, right? For money. And but for training the deep learning recommendation model, DLM, it involves all-to-all communication, because I'm not an expert in the DRM design, right? So I learned that from there, like study. So it has like a different distributed embedding tables, because embedding table is large. So it has, for example, in our like evaluation, there are like 26 embedding table to represent different attributes of the items of the users, right? So oh, by the way, the recommendation, the problem is like you have like a item item user table, right? And you want to recommend the item to different user. You want to scoring that, right? So as high scores will recommend this item to you, right? So, but to do this like a large embedding table, you have multiple different attributes embedding table, and this table are terabytes, so or some petabytes in the meta system, right? So it needs to read from like the distributed like a database and to load into the GPU memory, right? And then the data will need to you need to look up the embedding table, right? And after that, you want to feed the look up the data to each GPU for training for the top MLP model layers, right? So in order to do this like EMB embedding the table lookup to feed into the top MLP, you have to do an all-to-all communication. So that's the assumption. The details, I'm not going to talk about that, but we can discuss why this is an all-to-all communication. But the general idea is that different table has a different user, right? And the different table has been distributed on the different nodes. So if you want to collect the same users, like a different table information, right, you have to do an all-to-all communication, right? So, but all-to-all communication in the high-performance computing area is the most expensive communication in the MPI, for example, right? Because HPC people are using MPI. So all-to-all communication is challenging because you see every device is are involved, right? So based on our profiling, this is our profiling result on our system. It could take like more than 60% of the overall time to do the embedding all-to-all communication. But it's a little bit higher than the profiling result in the Meta own like system. So their system, I think, because they have a very fast node-to-node interconnect, and they are like a topology has been optimized for the all-to-all communication. Our supercomputer, we are providing that on our Big Red supercomputer at IU, right, at Indiana University. So they are like a result showing more than 40 to 50% of time doing the all-to-all communication. For example, using 128 nodes, right? And every node could have like a 4 to 8 GPUs. So the state-of-art approach to reduce this time overhead. So you can see like if we can significantly reduce this communication time, you can significantly boost the overall DLM training, right? But the current approach, I think maybe you can imagine that how people do that. For example, they are doing the quantization, right? So they are trying to use a mixed precision. They are using the half precision 16-bit with a single precision FP32, right? To mix the training that, and for communication, they are trying to use a half precision to do the communication. But this communication cost is still high because you see like 32 to 16 is just a comparison of 2, right? It's very limited. So their idea is can we use lossy compression to reduce the data, embedding table size, and then do the communication, all-to-all communication, right? And for this project, firstly, we try our existing lossy compression like SE or ZFP. And at the beginning, we thought like the compression ratio is okay, right? For example, 13 or max, and the average is about 6 to 7. But the problem is that if we want to speed up the communication, it has like some balance here, because you, as I mentioned, you need to pay the compression overhead or time overhead, and you gain some like data movement speed, right? So here like some heat map, right, to show that you have to develop the compression with a higher ratio and also higher speed, but sometimes you cannot achieve them both, because sometimes higher ratio means that you spend a lot of time in compression, and then the speed will be lower. So the problem here is like SZ compression, the ratio is not high enough. It's okay, maybe achieve 2 or 3 times speed up for communication. But if you want to achieve more, you either increase the compression speed or increase the compression ratio, right? So this is a thing we want to optimize in this project: increase the speed, increase the ratio, right? But before that, we are trying to augment the current all-to-all communication with compression. The idea is pretty straightforward, right? But here one note is because you are doing compression, so originally the data size is changed, right? Because after compression, you don't know the size, right? After compression. So you first have to communicate the compression size to set up the all-to-all communication, right? And then you can do the all-to-all V communication. So this is our overview, right? First, we augment all-to-all V with compression, and then we need to improve the lossy compression algorithm for embedding the vectors. And then we need to do adaptive error bound configuration, because different table had different sensitivity for the accuracy, right? And the next final step is the GPU compression performance optimization. The strategy or the methodology or philosophy is very similar to the first work, right? So you have to control the error, you have to augment the original system pipeline, and you have to theoretically, empirically analyze how we can control the error bound, right? And eventually you need to optimize the GPU performance kernel, right? So this is the pipeline I just mentioned, right? You first need to send the metadata, compressed sizes, and then send the compressed data in the tensor format, right? You can decompress that on each rank and use the data. This compression, all-to-all with lossy compression is not complicated, but at the beginning we thought like the metadata communication may cost a lot, but eventually we find the metadata is small, so just the scalar for different for one scalar for one process, right? For MPI or like a rank, right? So it's okay. And then we are trying to explore the embedding data features. So the embedding data actually has some very interesting features. So first, it's like a vector-wise data rather than point-wise data, right? Because every time you trying to look up or query one vector, right? So the data is organized in the vector-wise. And the frequency of each queries are extremely unbalanced, because some data are frequently queried, some data are just, not that frequently get, right? So you can see there is like a power law distribution of the data set, right? So some vector are highly used, some data are not that. So that's also the motivation for some other work. Probably if you quickly in Google Scholar, you search like DLM training, you probably find some like a caching like design. So those design also based on this motivation, because some vectors are frequently used, frequently looked up, so you can put those like vectors in the caching, right, in the cache system. So the cache system can be designed in the SmartNIC or in any maybe places, right, to reduce the data movement. So this is the motivation. We are using the same motivation, but this motivation is used for our compression design, because if some vectors are highly frequently used, right? So we can compress this data with a less bit information, right? So very similar to Huffman encoding, right? So if the data appears a lot of times, you just use less bits to encode that. That's a similar philosophy. And also values in each vector are non-smooth. So that's our motivation to design a compression algorithm. So then we are trying to propose an algorithm. I'm going to skip this part because it's a little bit too detailed, but the idea is like we can leverage the different occurrence of the vectors, and we are trying to identify those like repeated vectors and to increase the compression ratio, right? And to implement that, we have to have like a good GPU LZ algorithm. LZ is a compression algorithm that can identify the repeated pattern. And the next question, as I mentioned, we always try to play the trade-off for the error bound to control the accuracy, right? So we identify some table as sensitive, some table are not that sensitive. So we are trying to propose a mechanism to control the error bound for different tables. And this is a GPU performance overhead analysis optimization. I'm going to skip that. I'll give you some idea about our performance expectations. So we have to integrate these things to their like a production system, but we have like open source the DRM code that we can do some like prototyping and investigation. So here you can see that the original SC or QSC or QZAP, right? Their compression ratio is limited. Their speed is good. But overall, they are like a compression communication speed up is a 3 or 4 times, right? But as because we significantly advance the compression ratio, and also we can achieve some similar compression throughput, and over communication speed up is higher, and we can probably reduce the maybe 50% of the communication time to 10%, right? So overall, we can achieve maybe 1 point something performance speed up for end-to-end, right? And also this is the accuracy evaluation, because people, I mean, the first thing they ask the question is, okay, so if you are using lossy compression, do you hurt my recommendation result? So the answer is almost no, right? So because their requirement for the accuracy difference is sorry, is within 0.02%. So this is a difference accuracy delta between original and the compression-based solution, right? You can see that our difference is almost maintain their like requirement, right? So the difference is pretty good, and which means that our strategy is usable. So I think the team, Facebook team, is also investigating different like quantization approach. They are trying to aggressively use like quantization int8 or p8, or even like their own invented MX6. I think it's some format, and they are using a similar accuracy investigation approach, right? Try to control the original and the compression based solution within 0.02%, right? This is like a requirement. So that's why I say like we have to deeply collaborate with the team to understand their like a compression requirement. Then we can design a good approach. I think probably I should quickly close the talk, but this is the last work. I want to very, very quickly mention that. So the idea is like, as I mentioned, right, when you train a distributed neural network in the HPC system, the data is not in the local disk, right? So the data is saved in the remote file system, right? So if you have some experience using HPC system, right? So loading those data to the CPU memory, to the GPU memory is has a long latency, right? And considering many data parallel scenarios, the data is randomly shuffled, right? So you have to yes, you have to fetch the data from the PFS, parallel file system, to the host memory, then to the GPU memory, right? So it's very challenging. So we propose some approach to to mitigate this problem. The first optimization is that we are trying to maximize the data reuse, because when you read the data from the PFS to the GPU memory, the next time you don't really need to read all of the data. Some data can be reused, right? And we identify that you can change the epoch order or the data order within the one batch, right? So these are two orthogonal approaches. One is change the epoch order, right? Some epoch should be read first, some epoch, I mean, could be changed, right? So to actually increase the data reuse probability, and also within each batch, you can switch the data, right? So which can increase the data reuse, but has a minimum or no impact on the training accuracy. And the second optimization or observation we find here, like for the large data set training, the computation imbalance is less harmful than the IO imbalance. Because the current framework is try to balance the computation for each GPUs, right? For example, each GPUs evenly get like 32 or 128 samples during the training, right? Because they are trying to balance the GPUs. But our identification is like, our observation like, for these cases, the IO could be imbalanced because some data needs to be reread, some data doesn't need to be reread, some data needs to be read. So different GPUs could have like different IO or data loading latencies, right? So those like IO imbalance is really harmful for the overall training performance. And our strategy is that can we just slightly change the number of the samples in each GPUs. For example, some GPU could have 16, some GPU could have like 20, some GPU could have like 24, right? But their like IO reading time would be the same. This is something we want to argue here, right? So, and we propose some strategy to balance IO rather than slightly sacrifice the computing balancing, but without hurting the overall performance. And this is the second one, right? Oh, there is another one, the third one, aggregation trunk loading. I think this is pretty straightforward because when you read the data sample, it could be from the different positions in the file, for example, HDF file, right? Save the different samples, but read them one by one, one sample by one sample is really a performance nightmare, right? So we want to aggregate different samples. Sometimes even the data within the trunk is not needed. We still read that because we want to do the aggregation trunk loading and improve the performance. And you can see this is different IO reading pattern. You can gain some performance if you do a better IO aggregation and reading. So here are some like performance evaluation. Not going too much in the detail, but the idea is like after you optimize that in the different data set and in the different system, some low-end, high-end systems, it can all improve the performance compared to the PyTorch original data loader and to some other state-of-art work. And our investigation of because epoch order reordering, right? People will think about, okay, so it may hurt the accuracy, but our experiment results demonstrate it doesn't significantly reduce the training accuracy, sometimes even increase the training accuracy because we reorder the epochs, change the randomness of the data, right? Okay, so I think Solar has no significant impact on the final accuracy. That's our conclusion. And but here I want to say that this is kind of like the work has some limitation. We are not trying to replace the PyTorch data loader. We notice that this work really needs to have the data to be shuffled and also needs the data to be significantly large. That needs to be saved in the parallel file system because a lot of cases, the training data is only maybe several hundreds of gigabytes or like 1 terabyte. They can be saved in the local storage, and the different nodes can save exactly the one copy of the data. Then you don't have this problem, right? Because you have the data duplication. You don't have like a data shuffling, then problem solved, right? So I want to mention like this work has some specific assumption. We are not trying to replace PyTorch, but in some large scale AI for science training scenarios, we are trying to advance the IOs. Okay, I think that's my talk, and thank you so much for your time. And I also want to acknowledge and appreciate my students' like effort. And if you have any questions, so I'm happy to discuss. Thank you.
Thank you, Dingwen. Thank you for a very wonderful talk. And questions from the audience. So you can unmute yourself or input your questions in the chat box. I think I can start by asking some questions. Yes, so Dingwen, so I think in your last part of work, so you mentioned that so the bottleneck is that when we want to perform such distributed training in the HPC system, right? And so we talk about some of the bottleneck that for the data movement from the file system of the HPC, right? I was wondering, so whether it can be also applied to such kind of non-HPC system for the distributed training scenario.
Oh yeah, definitely. I think this is a very good question. So I think we also got some feedback from reviews when we submit the paper. So yes, I think in the cloud system, in the cloud platform, it's the same thing. And I think the problem even getting worse because in cloud, the data is saved in a totally separate facility could be, right? So for example, the AWS S3 or like they're like a storage system, and they are like a cloud instance, computing instance could be sitting physically or geophysically in different locations, right? So the data movement between the storage part and the computing part could be the latency could be even larger and the bandwidth could be even limited. So I think this is true and a good suggestions we haven't experienced on the cloud scenario. But I think the problem is the same, right? Because our assumption is pretty general, just assuming the data and the computing, I should say like how people describe that. This is the server, right? So, or I mean parameter server. So those sides are separately in the system, right? So saving the data storage system and the computing processor for the model are different part. So if we have this assumption, then the problem is true for different platforms. Yeah.
So then how about like if I if I want to do some like the distributed training locally for some smaller scale size distributed training?
Yeah, I think that's the point I just mentioned. So if you do not have a very large data set, right? Or I mean, your training is most likely bottlenecked by the computation and the communication. For example, in the NLP, right, model parallelism cases, I think their data set is not that large. They're just like some text scripts or something, right? And they are like communication is a bottleneck, and the data can be cached, saved in the local disk. And I would like to say this work is not designed for that, and could probably not working. Yeah.
Okay, so here you have some specific requirement that the data for the size of the data set, right?
Right, the size of data set, and also I think the model I think is I should say the model is somehow not that complicated, right? Because we are using the data parallelism here, and the model is not distributed. I think even the model is distributed, we can still have some benefit. But in this paper, we're very straightforward. We just assume the model is not distributed. We are doing the data parallelism, and the data is not saved on the local disk, and we need to randomly shuffle and fetch the data from the remote part, right? So no matter in cloud or HPC, yeah.
Okay, thank you very much.
Mm-hmm.
And questions from the audience? You can unmute yourself.
Yeah, I spent some time describing the compression, but for the distributed training, I think the main focus here is like the data moving challenge, no matter node to node or like node to disk, right? And sometimes it's a GPU to CPU. So I think in many cases, right? So if you face like saving the data challenge, the compression could be considered. Not only lossy compression, right? Sometimes we started with a lossless compression. For example, I'm currently collaborating with ByteDance. They are trying to use lossless compression for or reduce. I should probably add a little bit thing here is like they are trying to training large language model, and they are all reduced time for their tensor parallelism, for their model parallelism. Oh, sorry, for tensor parallelism is model parallelism, and for their data parallelism, they are using Megatron. So our performance results showing that the all reduced time overhead is larger than 40 to 50%. So they are trying to, but the reduction operation is for the gradient update. So they are not willing to use too much lossy compression. So we are helping them to use a quantization, just a very simple like FP8, FP16 quantization plus lossless compression. That's also possible. We see like the compression ratio is about 2 to 3 times, and we can gain something. So yeah, we are also working on the large language model training or reduce communication boosting. Yeah, but just for some information for discussion if you are interested.
Yeah. So following comments, so I was also wondering, so what have you ever considered, or is there some work that to apply those to the lossy compression on the model itself?
Yes, we have the first work, right? So the first work when I just started my career as a assistant professor, I had done a work, right? So called like a DPSE, where trying to apply the lossy compression to the model. And at that time, there's not much like transformer, those things, CN, right? So our observation is like CN, the storage demand is based on like a fully connected layer or like the top MLP, right? Those layers, but the accuracy is the major controlled by those like a convolution layer. So our idea is let's put the lossy compression on the fully connected layer, right? And then we do some like layer wise the error bound tuning or configuration. But that's a kind of like out of dated work. I didn't mention that today. I'm not sure for now, for example, transformer or like those attention, how about applying compression directly on that? That's a good question. So, but I have been not working on the model compression directly using lossy compression for a while, but it could be nice to rethink about that. Yeah, but that's yeah, we have some work 3-4 years ago now. Yeah.
And also, I was wondering, so for example, in your presentation, you mentioned that, and also some other groups work. So, like when we apply the lossy compression on the activation, like so we need first to compress that and then wait for the back propagation and then to decompress that. And I was wondering, so theoretically, whether we can like directly operate it on the compressed data.
Oh, that's a good question. So, that's yes. So I think it's very challenging, but we are trying to investigate that. If we, for example, there is like a compression called a homomorphic compression. So homomorphic compression, you think about compression as a function like f, right? So if you compress an array or tensor, it's like a fa, right? And you are trying to try to add another compressed data fb, right? So if fa plus fb is equal to fa plus b, then or like even smaller or not larger than there's some like a formula, then that is a homomorphic compression. Try to preserve the operation during the compression, right? That's your question. So I think we have recently identified some compressor has the potential to have these properties. We are trying to develop those like algorithms or modify existing algorithm to be a homomorphic compression. I think theoretically it's possible, but the challenge is like those compression could be with a limited compression ratio, and also like I think operated on the compressed data may also add some extra overhead. It's not directly compressed data plus compressed data. You need to compress data and the other compressed data, for example, you may need to do some like a exponential like alignment or some extra step, and then you can operate on that. But that's a very nice topic and idea. I think if we can make it a progress, then that would be a very nice, no matter the paper or project. But I didn't see too much like a point here. And also for information, like if we do the all reduce, for example, gradient descent, right? So you have the gradient on the different devices. If you compress the gradient after communication, you have to decompress the gradient and do the addition, right? Averaging. But if you have the homomorphic compression, you can directly operate on the compressed data, right? Without decompression. The benefit for that is first, save the compression overhead. Second is for the floating FP8, FP16, those like format, they have like overflow problem. So if you multiple times the compression, decompression, then it may not be able to handle those like error propagation. But if you can just operate on the compressed data, then you don't have this problem. So there are benefits, but I think we need to deeply collaborate with some theoretical people, theory people, or information encoding people, like to see, okay, if this algorithm is a homomorphic compression or not. But this is a good topic. Yeah.
Yeah. I think we can discuss it offline. Yeah.
Yeah, definitely. Yeah.
Yeah. So, okay, I think there's some
question in chat. Yeah.
Yeah.
In terms of the compression techniques, can we say that the lossy compression is one of the best to use? Also, is there a standard compression ratio when using it? Okay, so for the first question, yeah, that's a nice question. I hope like lossy compression is one of the best to use, but to some people, I need to spend time to persuade them to use lossy compression. It's similar to like the pruning, right, or model compression, right? So I think now more and more people adopt like you know, they can use a compression for the model in inference, right? But compression for training, I discussed with the meta people, they still hesitate, but they believe more and more people will you know, accept that, right? Because the story was like several years ago, meta people, even they do not want to use pruning or model compression for hardware inference, right? But now they accept that. So I would like to say, definitely, I believe lossy compression should be like the future, one of the best to use. But for different application, some application really needs like a FP64 or some high resolution. I would say we can work together to see lossy compression is okay or not. And for your second question, the standard compression ratio, that's a good question. So I would like to say for lossless compression, usually it's around 2 or less than 2. But for lossy compression, you can imagine more than 10 times, let's say 10 to 20 times. Usually, right, typically. And for some like extreme case, it could be like more than 30, 40. But generally speaking, it's imagine 10 times. So if you need 10 times of compression ratio and the lossless is 2 times, it's good for your use cases. You can think about trying it. Yeah. I'm curious about compression with regards to the time series data. Would it be required to the time interval first, or would it uncorrelating the data already achieve this? I think I'm not sure if I understand your question completely, but I would like to say like the database people working on the lossless time series compression for many years. So there is some like famous time series compressor. I think now there is some like lossy compression, but database people usually start with a lossless compression, and their data most likely is time series data. And they have some compressor called Gorilla. You can find that quickly. Gorilla is a famous one in the database community, I think, open source. And they consider the time domain correlation. And I think the point here is like if you want to compress data across different time step or time points, right, time intervals, right, you have to save those data in the memory. And sometimes in our scenarios, we don't really want to, for example, in the COMET, in that work, if you want to use the previous activation data to compress or predict this time step data, then you have to save the activation data for different time step that also increase your memory pressure, right? So using the time interval like correlation is good. Sometimes can significantly increase your compression ratio, but the downside is you have to save the data across different time step for prediction, right? Those is another memory overhead, but depends, right? So if you don't worry about your memory overhead, you want to just save the storage, then saving the time interval. Data across different time interval, right, can help you to increase. And the prediction is similar, right? Just think about the time domain is another point, right? For example, 4D data, 3D could be the spatial, 1D could be the time, right? So that's a 4D data. In HPC scientific computing area, like a 3D, 4D, even 5D data is a common thing because there could be 1D, the time domain. Yeah.
Yeah, other questions from the audience? Okay, so if no more questions, so let's thank our today's speaker again. So thank you, Dingwen. So thank you very much for the presentation. Actually, I enjoy our discussions very much.
Thank you.
I think we can discuss offline later.
Yeah, so we can discuss offline, and we can try to think about something to do. And some work we should like rethink and try to see some like a new, because the AI community evolves too quickly, right? Some works when we publish that after several 1-2 years, it's been very updated, out of dated. So we have to rethink about that. Yeah. Thank you for your invitation. Yeah.
Okay. Okay. Also, thank everyone to attend today's seminar, and see you next Tuesday. Okay.
Okay. Bye.
See you. Bye.
Bye.